or Sally, or Jaron, or Toussaint. Okay, today we are going to talk about work and energy. So we had work introduced in class and energy introduced in class yesterday. And you're good, you're good. That clock's actually a little bit behind my tablet, but we're still good. And we saw the definition of work that was, who remembers the definition of work? The mathematical equation.
Force over distance.
Not over.
Well, I mean over like multiplied, like the force acts over a distance.
Okay, yeah, force acting over a distance. Okay. So the mathematical relationship in calculus is work is equal to the integral of force vector dotted to dx. Remember, I wrote that down yesterday just to have it there as a reference. So the integral of force dot dx, integral means we're adding up over each of the tiny little pieces of motion dx. What does that dot mean? It's a dot product, which means we're multiplying just the parallel parts of those things. So it's a little more complicated because we have to think about that directionality. Now, what we're going to do in class today is going to be limited to some simple cases. We're not going to do anything that requires complexity in our algebra here and calculus. Now, work is always going from point A to point B, so I should have put here also limits from A to B. And in fact, on the next slide, I have the equation. Work is equal to the integral going from point A to point B of force dot dr. So we're going to apply this to, first, some common forces to find the work done by those forces. So the elastic force, the force that acts on a spring. The force that acts on a spring is minus kx. So let's imagine we have ourselves a spring. And here's the unstretched spring. And so with this unstretched spring, we are going to, so Hannah, Sally, and Jaron have arrived. We're going to take the spring, and now we're going to stretch it. And so I'm going to take the spring and stretch it out. So in the end, it's going to be like this, right? Now, what direction will the force the spring applies to an object be? If I stretch the string, what direction is the force going to be? Okay, you guys are pointing the correct direction. I'm looking at this, which is, of course, the opposite. I'm like, wait, I would have thought they would have understood that, and you did. So the force from the spring is pointing this direction. That's why there's the minus sign there. Because when you have your delta x going to the right, then you're going to have your force going to the left. So now if we're going to calculate the work done to stretch from some initial length to some final length, how does the direction of my dx, now I put a delta x here in this equation, but what is dx's direction going to be when I'm doing my calculus here? I will define, for convenience, my x and y directions as, So what direction is dx going to be if I stretch that spring? Okay, by definition, the dx is going to be in the positive x direction. Now, I can have my limit such that I'm going the other way, but by definition, it would be that way. And once again, I saw your finger pointing, Ann, and I was like, no, oh, wait. Yes. Okay, so the dx is going to be the right, and the force of the spring is to the left. When I do then my integral from a to b of f dot dx, I have putting it in using I hat to mean a unit, well, what are you more comfortable with? I hat to mean the x direction or x hat to mean the x direction? I'll go whichever one. What'd you say?
X hat.
X hat. So actually, before I do this, I'm going to write down the force of the spring vector is equal to minus kx in the x hat direction. Right, the x vector was x hat. So, and dx is equal to dx in the x hat direction. So what I've done is I've put the magnitudes out front and then the direction. Actually, I shouldn't say the magnitude out front if I put the minus sign there, because the minus sign really goes with the direction part. So when I do my integral, the things in parentheses are the vector parts. So I can take the non-vector parts and separate them from the vector parts the way I've written this. And this is equal to, and let's do everything we can to simplify. So let's bring anything that's constant out front. What is constant here? K. Because the letter K stands for constant. So that's a good sign that it's a constant. It's the only thing that's constant, A to B. And then I have the things that have vectors, minus x hat dot x hat. And then the things that didn't have the vector sign anymore would be x dx. Now, make sure we understand unit vectors. X hat means it has a direction parallel to the x-axis and one other thing. What's the one other thing? It's called a unit vector because it's 1 unit long. So the magnitude of x hat is 1. So if I have how much in the x direction with a magnitude of 1 times in the x direction with a magnitude of 1, what do I have when I do that dot product? I have 1 in the x direction times 1 in the x direction. 1. And it's a scalar product. We don't have a direction after we've done this. And so this part here would just be 1. And if you've done any work with this, it's super trivial, but I've got to cover it for people who haven't. So x dot x is just 1. I have that minus sign. And so this is minus k integral from a to b of x dx. I brought the minus sign out. The x dot x was just 1. And yeah, I saw you running to get here, Chad. And now we just have a simple integral. I believe everyone can do this integral here, so I'm not going to ask. I'm simply going to say now, I just said A and B. A is the starting point, B is an ending point. And so now when I put in my limits, I would have this. So here is the work done by the spring when I move from point A to point B, from XA to XB. Now we have the minus signs. The minus signs are there because the spring was doing a negative work. So going from A to B, if A is a smaller value than B, then you will have had a negative work done by the spring because the spring was pulling opposite the direction I was pushing, or I was pulling. So that's how we can calculate the work done by the spring. Now, what if I want to know, instead of the work done by the spring, the work required to stretch the spring? Well, opposite sign. Yeah. When you do a scalar, it's not opposite direction, but opposite sign. The force has opposite direction, and that's what changes the sign. So the work to stretch it would be the opposite. I would have to do a positive work to stretch it. Now, based on this equation, we say that the spring, because it took away energy when I stretched it, we say the spring stored that energy. And so we define a potential energy equals minus the work that was necessary to stretch it from its unstretched length to its final length. So that'd be the work going from 0 to B. Right, not A to B, because A is 0 for defining the potential energy. So if I just take the work I just did, and I put in 0 for the A, XA, I would have this is equal to minus, parentheses, minus 1/2 kxb squared, or 1/2 kx squared for the general equation. I dropped off the b to make it general. So the potential energy stored by the spring is a measurement of how much work I had to do to stretch it, and thus how much it will be able to return if I let go and let the spring snap back. So the spring, we say, stores energy, and we call that storing of energy potential energy. And so I was able to now calculate the potential energy equation for the spring, starting by calculating the work done by a spring when I stretched it. Go ahead.
That's the potential energy that we put into the spring, right?
Right, this 1/2 kx squared is how much potential energy the spring is storing, and how did it get it? Because I put it in.
What you've done.
Yeah.
So that first, like, the book showed it with like x odd and x final kind of thing.
Yeah.
The 1/2 kx odd is just kind of how much potential energy the spring has without us messing with it.
Well, without us messing with it, we, if you look in the lab guide, I was actually fairly precise in how I laid it out in the lab guide. The spring, we define an offset of 0 potential energy stored in the spring when it's at its equilibrium length.
Right.
So if we don't touch it, it has 0 stored.
So by convention,
Yeah.
we're calling that 0, and this is what we've added.
Yeah. The 0 points is something we don't emphasize a whole lot in general physics. We just say, well, for the spring, since it's a 1/2 kx squared, the 0 point for that equation is the position we're going to say is 0 potential energy, and we just say, okay, so that unstretched length is the definition of where 0 potential energy occurs. Like I wrote in the lab guide, you could have used something different for your reference point. It just makes the math more convoluted, and we don't want to do that. Question?
So is the potential energy after it's stretched?
Well, it's the potential energy at any time, but you just have to remember that the x there meant the amount that it's stretched. So it's not the length of the spring, it's the amount the spring is stretched. So if x is 0, if it's unstretched, then the potential energy stored in it is 0. But of course, the spring is never going to have an actual 0 length. That's the unstretched.
And work AB is when the spring is, it's the work done by the spring.
Work AB was the work done by the spring to go from position A to position B. So that's an example with the first of the forces that I listed here. This was a force that varied with x. Now the second one I'm going to go to is the force of gravity if we're on the surface of the Earth. Remember this equation, force of gravity is equal to minus mg in the y-hat direction. That only applies if you're on the surface of the Earth where we teach treat. G is a constant value. So this is for on the surface of the Earth. As you can see, the following equation is also the force of gravity, and that's the force of gravity equation that works at any time, anywhere. And of course, somebody might say, well, why worry about the special case when we have the general case? The reason is the special case is a very simple problem. The special case is a little more complex. It's not hard, but it's a little more complex. So we're going to do this one first, then we'll do the final one. So, starting with our equation, force of gravity is equal to minus mg y hat, or if you prefer, mg in the minus y hat direction. That's assuming vertical, y is up, and so gravity is down, making that assumption. Go ahead.
That confused me in the previous one. We could have, earlier we called it negative x hat. We could have called it negative everything in front of that with a positive x hat.
Yeah.
Conceptually,
Yeah.
it's the same.
It's better to write it this way than this way technically, because I have in the parentheses my direction. The minus is part of the direction. Right? The magnitude, remember, g is always a positive value because it's just a magnitude. And the m is a positive value. And so the mg is the magnitude of the force, and then the minus y hat is its direction. So it's better to write this way. And they're both accurate. They're both correct. Okay, so now we're going to have a situation where I have something like, here's the Earth, and on the Earth I have a red box, and the red box is raised from some y0 equals 0 to some y final equals height h. And I'm going to calculate the work done by gravity on it. So if I'm going to calculate the work done by gravity, what is my starting equation? Any one of you could answer. Work is integral, yeah. And then I'll substitute my force equation. Instead of putting A to B, I'm going to go ahead, especially because it's once again lost finger sensitivity. I think that might be something using Miracast instead of Chromecast. So once again, just like before, I said dy vector. This was dx vector over here. The dx vector is actually my distance I move, whatever direction it is. So for this case where we're moving vertically, I have my dx vector is equal to dy y hat because we're doing a vertical displacement. So now if I do the calculation, since it's lost finger sensitivity, I can't scroll effectively. Just in case you care, I have to press a button now to scroll. I do have it set so after I scroll it come back, but I forgot. Okay, so now that I have this is equal to minus mg, that stuff's all constant, integral from a to b of y hat dot y hat dy. What's y hat dot y hat? 1. What's the integral of dy? And so I'm going to start from, and I'll put y0 to y final because that's what I had put on my picture. So my A was y0, my B was y final. And so I get here, the work going from A to B was equal to minus mg y final plus mg y initial. Or since I gave those values For this problem, it would be, well, actually, let me leave it at that. So that's my work done by gravity here. Once again, if I started at a lower elevation, so y0 was lower, ended at a higher elevation, so y0 is higher, what's the work done by the force of gravity, positive or negative? Negative. So the work done by gravity, if I raise the box, is going to be negative. Of course, the work done by me is going to be positive, the same amount. If I let go, what's going to happen to the box? It's going to come back down because of gravity. So the force of gravity did a negative work when I lifted it, but then it's going to do a positive work to bring it back down. So once again, that defines what we call a conservative force. Conservative forces are named conservative because they will return the energy that you put into them. So with the spring, I pulled the spring and I did work on it, or it did negative work. If I let go, it returns all of that energy. And so it's conservative because it returned it. It just stored it. So we define this potential energy. It's the ability to do work. Energy, ability to do work. Potential energy is the ability to do work because of the configuration. In the case of the spring, it's because of how much you've stretched the spring. In the case of gravity, it's how much you lifted the box. But it's going to return it, so once again we'll say the change in potential, oh, I hope I put change in potential energy on the previous. Did I put change in potential energy, or did I just make a mistake and put potential energy the last time I did this? I've got to go back because if I made a mistake, that's a horrendous mistake that has to be corrected. Remember I told you I have it, so it's only a one-time use. Okay, yes, I did not write it correctly last time. I will put it here in red, so if you go look at my notes, of course, if you watch on YouTube, you'll see I made a mistake initially. It's very important that the change in potential energy is defined as minus the work. Potential energy is, shall we say, state variable. Or not state variable, state quantity. It's a quantity you have in a different state. Work is a process quantity. It's a quantity that occurs going from one position to another, for instance. So it's very important to have that delta there, and I forgot it. And from this, the outcome of this was that potential energy for a spring was equal to 1/2 kx squared. That was the key outcome, but no, this here is potential energy. This one here is correct, but the definition of change in potential energy is minus work. That's the definition of potential energy. It's defined by its change. Yeah.
Is the delta only going away because the convention that it's 0 to start with?
Yes, that's right. The delta is going away with the convention that we're going to start at unstretched length. And that's zero potential energy. So that's, we could have done what we call a gauge transformation and transformed to have a different zero position. It wouldn't have changed our physics, it just would have made our math harder. Okay, so change in potential energy, getting back to where I was, change in potential energy is equal to minus the work going from A to B. So that would be mg y final minus mg y initial. And so just like before, we define, okay, based on this, clearly potential energy must be equal to mgy because we're just doing potential energy final minus potential energy initial. Except for there could be a constant offset. It could be potential energy is mgy plus some constant. And so we define again potential energy due to gravity is equal to mg, and we often put h for height. And I'm going to do one more calculation just to make sure we're clear on why it's h for height. Why I changed from y, which of course meant elevation, to h for height. With the potential energy for gravity, you say, well, what height is going to be zero potential energy then? And it's up to you. Remember, I said there would be no difference if I had mgy plus a constant, because if they both have plus a constant, they subtract out. And so you can have any reference point for where zero potential energy is, and since this is linear, it's not mathematically inconvenient to choose some other reference point besides, one specific one. So you choose what's going to make my problem easiest. Basically, you choose a height that will allow you to put potential energy as zero at this location. The way that's going to make it the least amount of math for you, and you choose that to be your reference position for heights, and then any other height is just measured up or down from that position. Now, the reason I have the height in there, let us change the situation from what I started with. We have the Earth, we have a box, but now I'm going to raise the box like this. So the box changes from x initial equals 0 to x final, and from y initial equals 0 to height is equal to y final. And so I have some angle here that I could define. I'm just going to call this angle theta for now. And if I do my dx and my dy, right, my dx vector is going to be what component, if my dx vector is going like this, then how much is in the x direction? If I have that angle theta. Well, for the x direction, it would be cosine, because that's the adjacent side. So I would have cosine theta dx plus, and in the y, x hat. And then in the y direction, what would I have? Sine theta dy y hat. So that's what I would have for my dx, my vector displacement dx, in terms of this component and this component. Now, if I go to my integral, hey, it's starting to work on the finger again. Comes and goes. If I put it like this, now you see, well, I could break that up into two integrals. One integral is going to have y hat dot x hat. What is y hat dot x hat? Well, no, just going back to the meaning of a dot product. What does it mean to do a dot product? Multiply parallel parts. So what is x hat dot y hat? Zero then. So this dot, this is 0. So I can just put a 0 through this because of the dot product. Right, this value is not 0, but it's perpendicular to that. And then this one here is y hat dot y hat. And so I have yeah. Since my angle was considered constant here. I have this. And then you say, well, it's not the same as what I had before, right? It's not the same because there's the sine theta in there. But, oh, yeah. I make myself angry. I should have used an S here instead of X and Y for those. I should have used an S and just called this ds there to make it clear. We're integrating going up that path. I really made a mistake there in my terminology. All of the math looks right except for my terminology and the fact that I said this was dx and then I said dx and dy. It should have been ds for the length up the path and then the sine theta. Why is it important? Because when we do this integral, we get minus mg sine theta times SB minus SA. SB minus SA is the distance from here to here. So if I take the distance from here to here, multiply it by sine theta, I will have this side of the triangle, which is h. And so this combined together is, once again, h. And I meant to make it very clear, and because of my bumbling on the DS, it's probably not as clear. Question?
Where did the y go from, if you see where you have your from a to b negative mty y?
Yes.
Where did that go?
Okay. How about I'll erase from where I was not precise and just do it again. So we're going to travel up here, and I'm going to call this ds for the hypotenuse, because that's the path we're using. S is used in these cases to indicate it's some path, not in the x direction, not in the y direction. And that's kind of where I messed up, was by calling it x vector instead of putting just ds vector. I got myself confused. It is right to put dx vector, but I got myself confused. So my ds vector should be equal to, in the x direction, cosine theta ds x hat. See the difference? And in the y direction, sine theta ds y hat. So then when I do my dot product, the one with the y hat dot x hat disappears, and I'm left with force of gravity dot ds is equal to minus mg sine theta dy. And then I integrate that, and so I get my work going from A to B is equal to minus mg sine theta, and then I will just put in s, where s is the total distance going from here to here. So now I have, the triangle has s is this distance, but this distance of the triangle is our definition of the height, how much it was raised. And just looking at your trigonometry, s sine theta is height. And so it turned out that the work still only depended on the height. It didn't depend on the horizontal motion, simply because the force was vertical and work is force dot distance, so it's only the distance parallel to the force that mattered.
And that's only the work due to gravity, right?
That's only the work due to gravity, correct. Now we'll go to, okay, and so then potential energy. That's what you get when you put minus. And so we end up by defining potential energy due to gravity is mgh, just like I have in the box up above. Okay, now let's do the final one, the one with the true, always true force of gravity, which will come up here in just, excuse me?
Could you go back a slide?
I went back one too many slides. You mean back to where I just ended? Let me copy this equation so everybody can see it, and then I'll go there. I will copy it better than that. I know you can't tell that I did a bad job, or at least I hope you can't tell that I did a bad job, but I did. Duplicate. Okay, so I'm not sure what you want to see here, Hannah.
Just the last part. I can't see.
Okay. Okay. Finally, paste sesame. We have this equation for force of gravity. Now, I've written it two different ways. This is now written as a vector equation. I don't think we've talked about it as a vector equation. We've just said the force of gravity is always attractive, always pulls things together. It's proportional to the masses, m1 times m2, inversely proportional to the distance separating squared, so that's the over r squared. G is the constant proportionality. This here is clearly a mistake. That is supposed to be a G. I can't believe I didn't see that. Whoops. This here, minus r hat, is giving the direction. Because it's always attractive, we define the r direction as the direction pointing away from an object, and so minus r direction is going toward the object. It's a way of saying that it's an attractive force. So that's the direction shown in the first. In the second one, we have minus r vector over r. Notice this went from r squared to an r cubed. So you can see it written either way. It just depends on your preference which way you write it. This one here is generally the one we write. We prefer it because we can see it's inversely proportional to the separation squared. If you look at the one that's on the right, if you look at this one, you might forget that it has an r on top and think that it's inversely proportional to separation cubed. So that's why that's not generally the preferred way of writing. So I wrote it both ways because different textbooks have it both ways. Now we're going to calculate potential energy between two objects. So I have object 1 and object 2. And so if I look at, let's say, object 2, it's going to have the force of gravity pointing like that. So this pointing like that is telling us that our r direction is going like this because it's pointing in the opposite r direction. The r direction is going away from object 1. The force from object 1 is going back toward it. Now I want to calculate the work done. Let's say that I take this and I move it from here to here. So here I have RA and here I'll have RB. Now remember, R is measured as this distance. Using the same color for both of those, definitely a bad choice. RB. Okay, that was a BB. Okay, so I'm moving it from RA to RB. Now, what happens if I move it horizontal or tangentially instead of in the radial direction? If I move it tangentially, if I take this and if I displace it this way, how much work am I doing? None. Why is that? Okay, it's always the same distance. There's still a force, but I was perpendicular to that force, right? The motion was perpendicular to the force. So only the motion coming in or going out is going to involve a work. So I drew my picture with RA here and RB here. That's actually perfectly fine, even though they're different angles, because it's only the extension that matters. You have a question, Chad?
When you say that there's no work done moving it like that, you're saying no work done in relation to the force of gravity that we're talking about. Obviously, moving it would involve work. But
Okay. Yes. We haven't talked about kinetic energy yet. And so as far as everyone knows who doesn't know kinetic energy, that didn't exist. Yeah, if we change its speed, that also involves work. That's what you're referring to, right? So for our calculation of the work done by gravity, only getting closer or moving farther apart is going to involve work with gravity. So to do our calculation for work, we once again go back to our equation. I should just quit today. Now I'm using .dr because only motion that is in the radial direction that's going to be farther or nearer is going to matter. And my dr, since r is that direction, I'll have dr vector is equal to dr times r hat for my substitution. And so if I'm going to use that, the dr times r hat, clearly the first one is the one I'm going to use for the force of gravity. Keep the constant things outside the integral. So there I've taken everything constant, put it outside the integral. I have the stuff inside the integral that's not constant. Well, what's r hat dot r hat? 1. So this is just equal to minus g m1 m2 integral from a to b of dr over r squared. It's not a hard integral, but it's the hardest one of the day. Integral of dr over r squared you have r to the minus 2, you raise the power by 1, so it becomes r to the minus 1, 1 over r. And then we have to divide by our new exponents. We have to divide by minus 1. So writing it the way I said it, or putting it in something that looks better, we have that for our gravitational potential energy equation. So, or not potential energy yet, that's work. So that's how much work would be needed to pull the object away. Or excuse me, that's how much work gravity would do. You'd have to do the opposite. So based on this, we can say change in potential energy due to gravity minus work AB, and that gives us potential energy due to gravity is equal to, well, it's got to have this form, Gm1 m2 over r. This minus sign is going to put a minus sign here. Now, once again, you could have a gauge transformation, but it would make your math difficult. So we choose our reference point for zero potential energy to be the location, the r value, where this function here gives us 0. So what r makes this equation here equal to 0?
Wait, what r makes which equation?
Makes this equation right here equal to 0.
Infinity?
That's correct. So we use infinite separation as our reference point for zero gravitational potential energy when we use this form of the equation. Now, there are some things with this form of the equation that can really throw you off if you don't think about them carefully. Notice that we have, if we compare the two, potential energy. I'll change colors for curtains. Potential energy, if we have a constant g, is mgh, where h is our elevation above the surface of the Earth. So if you go up, what's happening to your gravitational potential energy? It goes up. Then we have potential energy, I use capital G to indicate I use the different one, minus capital G, mass 1, mass 2, over r squared. Nope, not over r squared, over r. By the way, you'll notice this over r looks like all we did was we took the force equation and multiplied it by r and canceled. Obviously, that wasn't right, because your distance you moved wasn't r. Right? Your distance you moved was a small percentage of r, probably, if you just, move things from being this far apart to this far apart. So it's not just a cancel thing like it would look like if you didn't understand calculus. And then you have the change, well, the sign issue. So now, as h increases, so let's say we're talking about the gravitational force between the same box and the Earth. As h increases, what is that doing to r? It's increasing. And what's that going to do to potential energy due to gravity? Okay, the magnitude is getting smaller, but the sign is negative. So if the magnitude is getting smaller and the sign is negative, it's getting more positive. But you have to think about that minus sign, because if you just look at the magnitude, you're all, uh-oh, it got smaller when I lifted the box with this equation, it got larger when I lifted the box with the other one. Can't both be right. But the key is, it got smaller magnitude in a negative value, which means it went upward, more positive. So these two equations are both correct. This one here is always true. And this one here is true on the surface of Earth. And one could say, well, I'm going to use the one that's always true. And you can if that is your desire. But it will make many problems much harder. So it's just a good, fair approximation on the surface of the Earth to use the upper equation. Now I only have 3 minutes left. Let me, go ahead.
One question for that first equation. Would that be true, like on other planets, if you had a different value for G instead of
Yeah.
G?
Yes, if you're on another planet that is large compared to any distance you're going to move up and down. Yeah. If you say, well, what about if I am on a little satellite that's, a mile in diameter? Well, if it's a mile in diameter and you jump up, you're going to go a significant fraction of that diameter possibly escaping. Because we're at the end here, let me just talk about a few things that this last thing is relevant. We've already used this. This was, I'm sorry, I didn't change that. A lot of textbooks use U for potential energy. But our textbook uses PE. So, same thing. When we talk about planets orbiting, Kepler had the breakthrough that planets do elliptical orbits instead of circular orbits. Now, if you have an elliptical orbit, you have, here's your star that you're orbiting about, and I believe I have ellipses actually turned off. Oh, no, I can do an ellipse. I better do the ellipse first, though. Well, that's not much of an ellipse. That ellipse doesn't go with it, but who cares? So there's my orbit. Now, that's a very eccentric ellipse. Eccentric, a standard reading of eccentric means not normal, right? Like, that Webb dude, he's an eccentric dude. Means he's a weird cat, right? Well, eccentricity is measuring how weird the circle is. This is clearly a weird circle. The more eccentric, the weirder. The more elongated, the more eccentric. Okay, Kepler's first law says that planets orbit in a... Got to change my tool. They orbit in an elliptical pattern with the sun at one of the focal points and just an empty spot at the other focal point. Ellipses have two focal points. Now, if we used what we just learned, what would you tell me about the potential energy of the planet-sun system when I have my planet out here? Okay, it's the largest distance away from the sun, and hence the potential energy is, it's the closest to zero. So it's the highest potential energy it gets because it's the closest to zero, and the potential energies are always negative. So that's the highest potential energy it can have. What's happening to potential energy as it comes closer? It does what? Okay, it gets more negative. So it's going down to lower and lower potential energies. So when it's here, it's at the lowest potential energy, and out here it's the highest potential energy. Now, something we didn't learn today that we'll learn in class tomorrow is about kinetic energy, about an idea that Chad brought up. Kinetic energy, the energy in motion, has to do with the velocity and the mass. The equation is kinetic energy is 1/2 mass times velocity squared. When it goes from this position to this position, it's lost a lot of potential energy. And I think it's 1916, Emmy Nether showed mathematically that our energy can't be created or destroyed. And so if that potential energy goes down, the energy had to go somewhere. And where does it go into? Kinetic energy. So if the kinetic energy goes up, what does that do to the speed? The mass isn't changing. So the speed increases. So this planet's going to go fastest when it's closest to the sun, slowest when it's farthest away. And it turns out that is Kepler's second law. Kepler's second law actually mathematically says that the area swept out per unit time is constant. So when it's farther away, the area like from here to here is the same as the area from here to here. So it'd have to take like a month to do that and a month to do this. But of course, this is a much bigger distance for a month than this, so it's going a lot faster. And so Kepler's second law relates the area swept out to the distance away, or excuse me, it says the area swept out per time is constant, area to time. It's another way of saying what you get with conservation of energy, that it goes fastest when it's closest and slowest when it's farther away. Both of them give you the same mathematical relationship for the speeds. And then his third law, Kepler's third law, we already showed in flip right. So it's 2 minutes overtime. Time to go.